So hi guys, I'm Tymoteusz, this is Tomasz. We are going to talk about recognizing products from descriptions, basically from names of the authors on our site. And I think most of the talks you will hear today would be some kind of success stories. In our case, we chosen like 2 examples from our daily work because we felt that they're a great example to compare 2 different approaches. So basically traditional machine learning, shallow machine learning, and deep learning. So like you shouldn't expect to see, I don't know, mind-blowing results, but we would rather focus on like differences between those 2 approaches. If you come from Poland, then you probably know Allegro. We are the largest e-commerce site in the region. Basically on our site you can find different sellers who sell their stuff. And it's like almost everything, starting from, I don't know, some small items, maybe fashion, ending up on, I don't know, computers, many different things. And one of the problems we have is that since there are many different sellers, the descriptions that they provide for the products vary in quality very much. Sometimes the descriptions are like very precise, sometimes they're really random. And we would like to identify the products. So first of all, because we would like to know what is being sold on our platform. Second of all, we would like to make good recommendations and like good, for example, good marketing emails. So we have like several results for this. And you can identify products using many different approaches. You can try using, for example, regular expressions. This gibberish text that you see on the bottom is a regular expression to identify this name of kind of car tires. As you can expect, this wouldn't work for many different categories of products. This is very limited, but in this case, it actually worked pretty well. So we tried machine learning.
So we had this problem, and we didn't want to approach it from a point of view of a classification of identifying a particular product, but rather seek to find a pattern that can be identified as a new product. This is because the product bases are quite limited and vary in quality and so on, and second of all, because there's new products coming up all the time. So we want to be able to look at the offer name and just see the pattern that will give us some idea on the product name. So we started this approach from matching the offer names with some product databases, and this way we got a view of a split offer name. Looking word by word, we were able to create a target variable actually by assigning a 0 or a 1 to each word. So this is something that we want to predict. Taking some offer name, we want to assign these values to particular words and then getting the product name in this way. So yeah, you can already see that, well, sorry for this being in Polish, but it's actually a screenshot from the website, but you can see the product name here is already quite noisy. Okay, so what we did first was to try to use a simpler approach. So this is a problem that for a human eye is quite well defined, and it's sometimes quite unproblematic to see some patterns, and well, you're able to develop some intuitions on what is important in this task. What can be some distinctive features for particular words. So what we did was to engineer some basic features like. Of course, offer category, because in each category there's some certain specifics of offer names, even though they are quite heterogeneous. Then we got to certain specific features of each word. So word length, is it a number or a character word, because we are splitting characters from numbers. What was the position in name? This is actually here in this example already quite visible. This is usually the case that, for example, the name is earlier in the offer name. It's not always the case, but we'll see. It's actually quite a good prediction method for this. So, for example, matching this with some brand dictionaries also lets us get some information. So these are some features of particular words, and what we wanted to see to get some context on each word was to get the same attributes of the neighboring words. So we got for each of these words we got the characteristics of the previous word, the next word, and so on. So there's no vectorization. We are only interested in features of these words. We're not interested in the words themselves, actually. So this was the initial input, and this actually worked for us pretty well, because the first attempt on doing it this way was to try and clean up a product database, a quite well-structured product database that is, well, a bit too difficult to manage by some heuristics, but there are some identifiable patterns that are not too complicated. So when we used this, we had a balanced data set, because roughly half of the words were actually these words that we are looking for, and we had just like 37K observations looking at word level. And yeah, we've run some random forest, XGBoost, and some simpler models, and without much effort we got to over 97% accuracy in test. Precision in Lico, you can see it all worked very well. So in a short time, without much computation expense, we were able to get a tool that worked really well for this kind of data. Yeah, and actually here we could see already that in this case, for example, the position of words was the most important thing for prediction. In case of offer names, this is much more complicated because we will be dealing with much more heterogeneous data. So actually, this kind of approach was something we tried to apply to offer names now. And the main algorithms that we used were random forest, and in order to make the computation simpler, we used extremely randomized trees, which are simpler mainly because they don't optimize the cutting point at the split. They just randomize it. But we found out the performance, the accuracy, and all the metrics are really similar, but the fitting time was like 3 times shorter. And actually, another thing, this was all trained locally on 70 million observations, I think, and this is something we could do pretty quickly. In case of memory problems on a laptop, this kind of ensembling worked really well because we were able to loop it, and well, it didn't make any requirements on special architecture. We'll see later on that this is something that we have to consider in case of deep learning, of course. So the results that we got here was 76% of accuracy by word. This is actually not really impressive. We will see that we can use very simple tricks to get to this point. Precision and recall were actually quite good, but what's important was that even though we got to 24% of perfect matches, so an offer was perfectly matched to a product. Each word was classified properly. When we set the threshold, the tolerance threshold to 1 or 2 words, we can get the coverage to 50% for one error per offer name, or in case of 2 words, almost 3/4 were correct. So, assuming that actually there's actually no one correct solution, this is something that was not so bad, so to say. Yeah. So now let's see. Our next step was to apply to this data another approach of deep learning, and
right.
Tymek will say something about it.
Right, so another possible approach is to use deep learning. Everybody talks now about deep learning, so we'll also talk about deep learning. This is not yet deep learning. This is something much simpler. Actually, we would like to use deep learning because we would like to work with raw text of the descriptions. But the problem is that every machine learning algorithm wants from us numbers. So we need to provide data in the form of numbers. One thing we could do is we could simply map each word to some kind of number, one-hot encode it, and end up with like hundreds of thousands of one-hot encoded vectors, basically. The problem is that this would also lead to like hundreds of thousands of weights in our network, and the model will be huge. So the one thing we could do is we can use feature hashing. It's a very simple trick. We use a hashing function. This is some kind of function that basically maps the words, takes any word as input and maps it to some number from a fixed range. So the problem that we potentially have is that we can have different words mapped to same number, and this is usually a problem in computer science, but actually it's not that much of a problem for machine learning. It appears that it works pretty well if we do like this. Sometimes it's work even better than using like only one-hot encoding on raw words. And what happens is that by introducing this kind of noise, we prevent models from overfitting. This was also the case in our example, because using feature hashing instead of some kind of tokenizing helped us to reduce the number of words, the vocabulary, like by half or something like this. At the same time, a little bit improving the performance of the model. So it worked. Like the most basic thing you do when using deep learning and when working with language, but also any other categorical variables, is we use embeddings. The basic idea of embeddings is that instead of using very long vectors of zeros and ones in one-hot encodings, we use shorter vectors of floating point numbers. So it doesn't sound very clever, but actually it has pretty nice properties, because by mapping those vectors to something shorter, first of all, what we see is that the vectors become meaningful. So the similar words are represented by similar vectors, and also we usually see quite nice relations between those vectors. So you probably heard about those examples where you can, for example, that sum of like king and male is something similar to sum of queen and female. You probably heard lots of those examples on other talks. So appendix is like the lowest building block for the network. And we tried several different architectures for this problem. We tried one-dimensional convolutional networks. We tried recurrent neural. Okay, I will start from the beginning. With one-dimensional convolutional neural networks, the basic idea is that we have some kind of sliding window that goes through the sentence. Let's say that this sliding window is of size 2, then it basically looks at pairs of words. And each of the sliding windows seeks for some kind of pair of words that it finds important. So with many sliding windows like this, we basically look for bigrams of words. Another architecture that we tried was architecture that was using recurrent neural networks. So the idea behind recurrent neural networks is that the network looks at some particular word, but also looks at the context. It looks at, it selectively can remember or forget what it was looking before. So it doesn't look only on words or on pairs, but also it can look at all the history. We also tried quasi-recurrent neural networks. So this is basically something in between recurrent neural networks and convolutional neural networks. And actually all the architectures worked really similar. There wasn't much difference, so I'm focusing right now on the recurrent neural networks. In this case, we used bidirectional LSTM layers. So this is the kind of layer that looks at the history, so the previous words, but it also looks at the future words. So it goes in both directions at the same time. Skip connections. So some kind of information flows into LSTM, something goes out, and then we sum the input with the output. This is pretty popular architecture for convolutional neural networks, but also for recurrent ones. It was trained on a single GPU with Adam optimizer, some kind of learning rate scheduling, early stopping, and several different tweaks. Now, if you would like to have some kind of intuition what the network was doing, and there is this picture, and what it shows what would happen if you would change some word from the offer name to another word, choosing at random. This is, of course, repeated many times and averaged. So what we see is that if we replace one of the first two words to something completely random, those first two words, if you don't know Polish, are male shoes, then it still thinks that the probability that they are part of the product name is 0. That's why it's black. And it still thinks that all the other words are almost surely product name. Now, if you change Reebok, the name of the brand, it was pre-processed, so you don't see the repeating character, but it's the brand. Then it starts thinking that, okay, this random word is rather not a part of product name. Now, if you change something from the middle of the sentence, then the network becomes it gets lost, basically. It starts thinking that, okay, maybe something in the end of the sentence is a product name. So basically those strange numbers and the jogger, maybe that's a product name. And and while changing like last part of the sentence to something random, it leads to makes this network think that the beginning of the name is a product name. So what we see is that the network doesn't look at the single words. It looks at the context, and it looks at some groups of words for sure. And sometimes it makes global decision, like in the third line from the bottom. Sometimes it makes very local decisions, like with the brand name. So it's pretty flexible, actually. Now, if we look at the results, as I said in the beginning, nothing impressive. The accuracy is 88%, precision and recall 80%. For 28% of titles, we had perfect match. So this is far from impressive. But I think that those numbers are not really that relevant for the problem. Because if we will look at what it predicts, then the predictions are really, really reasonable in most of the cases. That's not a metric, of course. But you can look, for example, how often does it predict very short names? And it doesn't. It predicts names that are like 4 words, at least 2 words. So it seems that it's pretty reasonable. Also, it rather doesn't happen that it doesn't predict anything. It happens with a similar frequency as in real data. And it has many, many properties that are very similar to the distribution of the original data from the training set or the test set. So this tells us that the distributions are pretty similar, nonetheless, that there are small differences that make the basic global statistics drop. Also, what's interesting is that if we use this algorithm and we predict the names of the products from our data set, then we see on average 3 distinct predicted names per product. In our data set, the one that we used for training it, we had something like 50 offers per product. So we reduced 50 different descriptions to only 3 different names. So that's actually pretty good. And what's even better is that the top of those 3 names was predicted for, on average, 64% of offers. So in most cases, we get only the single name per product and some noise at the tail. So that's not bad, actually. Okay, so we'll try to make some comparison between these 2 methods based on what we learned when approaching this task. So let's see about it. So there's actually plenty examples when neural networks are being overperformed by some easier methods. So, for example, there's this paper by Cheng, Homchuk, Matlov, and Mohanty from this year, when they make a comparison between polynomial regression and neural networks, and on actually several examples, then they demonstrate some even advantage of polynomial regression over neural networks. This is of course when we're dealing mostly with some tabular data. So actually in these simpler cases, so for example, we have this planes database here as the airline data set as an example. So there are some cases when we don't have to resort to such computationally expensive methods. We
we can actually get meaningful results from some less complex solutions. And this was actually the case for us with the first step, so the product database cleaning, where we got really good results without much effort and much computation actually. So to make a comparison between these approaches, we have the main metrics here. So the first one is just a dummy classifier of a global mean, so assuming all zeros. The second one, which actually performed surprisingly well, I think, was position-wide means, which in effect got us to selecting first 4 words from the offer name. And yeah, we've got almost, I think, 80% of accuracy. Well, we can see that the other metrics are not on par with the rest of what we've done. But still, it was quite surprising to see that. We can see that although random forest doesn't really achieve well even a satisfying accuracy, it tends to perform well similarly to neural networks in terms of precision and recall, of course. When looking at the results, we've seen that the neural networks made simply more sense.
Yeah, and I think one thing that we probably didn't mention is that the problem. I think that the reason that we had such problem with getting better metrics is that our data is very noisy. Yeah. What I mean is that first of all, the descriptions of the product by the sellers are really noisy. They can mention, I don't know, shipping time is faster from me, or you can get something for free if you buy this, or this is a very great offer, or some really different stuff. But that's not the biggest problem, because also the database of product names that we have is also noisy. It's also made by humans. So our labels are already noisy because of it. So we have noisy input and noisy output. So I think that's the biggest problem, because we are often, when we train those models, like both machine learning, standard machine learning, and deep learning, we are very often overfitting to this kind of noise in this data set. And I think this really reduced those metrics in pretty large extent.
Yeah. So to finish with a comparison of these two approaches, this kind of shallow machine learning was relatively fast to train. So actually, we found out that in case of the trees, we got to pretty fast. We got to a level when we got no additional accuracy growth in adding more trees. So it really didn't require much computation. The results can be good in cases when we have this intuition of what the tailor-made features could be, and when we apply this kind of domain knowledge. So our first use case proved that this can be done in achieving high accuracy. Of course, less computation. Out of the box, less hyperparameters, or almost none in case of this kind of trees ensembling. Impact of model choice and hyperparameters on results can be better understood. The case for interpretation also can be made. We saw from previous presentation that there's advances in terms of deep learning model interpretation. And what we've seen here, that it can be good for structured and tabular data. On the other hand, in terms of deep learning, we don't have to apply any domain knowledge in not as much. So we don't have to engineer features as much. We can provide almost raw data and get interesting results. The family of models is flexible. The performance tends to be good on larger databases. We actually didn't stumble upon much problems in terms of fitting it on large databases because the libraries are prepared for that. So yeah, of course, it has to get much data. So yeah, I don't know if I skipped something.
I think that's the most important points. I think that it's very important to pointing out that the biggest problem we had was overfitting to those random patterns in our data that were totally meaningless. And most time of the tuning of the model was about regularizing it so that it doesn't overfit. Yeah. And also, if something wasn't clear enough, then we provided some kind of links and resources that you can check out that are very clear, and I think worth recommending to get a better understanding of something that wasn't clear enough. So thanks.
One question before lunch?
Lunch.
There's one here in front.
Okay, hi. Thank you for the speech. You have amazing prepared. I have one question regarding word embedding. You have trained. Have you trained your word embedding from scratch using only an Allegro database, or maybe you used some external databases like Wikipedia or something like this?
We trained it from scratch. I know that there are other teams that also use deep learning in Allegro that use pre-trained embeddings. But my personal opinion is that our data set is too specific, and this kind of non-grammatical names, non-grammatical titles that sometimes have nothing to do with real Polish language, and they are very short. They use numbers, some strange symbols in the names. So I don't think that it would be reasonable to use pre-trained embeddings on some other data set. And also we have huge data set on our own, so we can train on our data set.